Bam! Mr. Tarrou, in this lesson we are going to define and look at the graphical attributes of exponential functions. Now we care about these functions because they model a lot of different applications in the real world. Population growth and decay, just about every financial formula is manipulation or some form of exponential function. And going along with that decay part of it, carbon-14 dating or half-life problems, where at least with carbon-14, they use that process to estimate the age of, say, fossils that are dug up in the ground by archaeologists. And now I've already done a couple of lessons on exponential functions. I'm going to put links to those in the description of this video. One is solving compound interest problems, so there's your financial type example. And another example down there, you'll find a lesson about carbon-14 dating. Okay, so what are exponential functions? Oh, you're also going to find a link to a lesson where I just give you an exponential function and we start graphing it and talking about all the different transformations. You know, if you know what the parent function looks like, then knowing if you see a plus or minus somewhere in the equation, that might move it left or right or up and down. And for an Algebra 1 lesson, that's a little bit beyond the scope of what we need to know right now, but at least you can see where this topic is going to come up again later in your studies. All right, so exponential function is a mathematical function in which the independent variable, that's the input variable, in word problems it's the variable that you have some control over quite often, appears in one of the exponents. And a form of an exponential function is y is equal to a times b to the x. Sort of a fairly basic form of this exponential function. And when you look at this a is equal to b to the x, now we have a variable in the exponent, but all of these, you know, are really variables. But we see that a and b, these are going to be real values, and a is going to be an initial amount of something. So like if we're talking about a money type problem, then a would be the initial amount of money that you're starting with, and then maybe if you put it in the bank or you invest it, it starts to grow over time by usually some percentage per 1 year period. Oh, and by the way, even though I'd hope you'd click on the links down below in the description of this lesson, continuous compound interest is y is equal to p times e to the rt. Well, there's that p, there's that initial amount, e. Though it looks like a variable, it represents a constant of approximately 2.718. And r is going to be the interest rate that you're earning on your money, if we're talking about compound growth. And there is our independent variable of time. You get to control how long that money is in that investment, just as an example. So it's a version of this formula we have up here, something times some kind of common base raised to a variable exponent. And with time, or with compound interest problems, that variable exponent is in number of years usually. Okay, so so a is our initial value, and b is what you're going to be repeatedly multiplying by. And if that base of the exponent, b, it might be a single number, it might be some kind of expression wrapped in parentheses for other types of financial type examples. If b, that base, is between 0 and 1, you're going to be looking at exponential decay. And if your base, again, of the exponent is greater than 1, then you're going to be having exponential increasing. Now, if these inequalities, these intervals describing what b can take on and when it's exponential decay and when it's exponential growth, you'll notice that nowhere here does it say that it's possible for this base to be negative. And you'll also notice that we have here b is less than 1 and b is greater than 1. Well, it wouldn't make any sense to be talking about exponential growth or decay or an exponential function if the base were equal to 1, because you would just be constantly multiplying by some multiple of, or you'd be constantly multiplying a certain number of times just by 1 repeatedly. Well, if you multiply by 1, nothing changes. 5 times 1 is 1, 5 times 1 and 1 and 1 and 1 and 1 is still just, did I just say that wrong? 5 times 1 is 5, and 5 times 1 times 1 times 1 times 1, I don't care how many times I say that, it's still going to be 1, because 1 is the multiplicative identity. Basically, when you multiply by 1, you don't change the value of your number that you're multiplying the 1 to. And I keep pausing because I want to stop and say, let's not forget that exponents only work on the base on which they're stacked on. So that x is only affecting or only applied to the base of b, not that initial value of a. Now, graphically, if your base, b, is greater than 0 and less than 1 and you have that decay situation, you're going to have a graph that is in quadrant 2 going to be approaching infinity. And as you read that left to right, it's going to be coming down from positive infinity, and it's going to be approaching a horizontal asymptote of y is equal to 0. And I wasn't sure whether I wanted to write this in my sort of like little basic diagrams or not, that it's going to go through the point 0, a. Well, if you let x equal 0, any number raised to a 0 power is going to be equal to 1, and thus you have a times 1, which is still going to be a. But if you go down to those lessons in the description of this, this video, this lesson, you're going to see that we can have we can have transformations. We can apply transformations, like we can move this graph down if there's a transformation which causes that to happen, like maybe it's a times b to the x minus 2, and that minus 2 would push this graph down, and thus we wouldn't really be going through 0a, we'd be going through like 0a minus 2 or something like that. So this standard point of 0a is only for sort of this basic form of the exponential function. And then if b is greater than 1, then we have a graph which is going up to the right. And by the way, this is going to be called monotonic decreasing, because as x increases, the y value never stops decreasing. And this is going to be monotonic increasing, because that, again, that base is going to be greater than 1. And assuming there's no other types of transformations, and there's more transformations than just moving the graph up and down, by the way. If you don't have any transformations like a horizontal transformation or a vertical shift, that point again is going to be 0a. Okay, now for exponential functions, the domain is going to be all real numbers. You know, as you see this graph, it's rising up to the left and it's going to the right, and there's no breaks in this graph. So the domain, if I look at every single individual point that makes up this graph, and there's an infinite number of them, each of those points has some kind of different x value, right? So what x values are included through each of the individual points that make up this entire graph? Well, that's going to be all real numbers, because it goes left and right forever. For the range, I always suggest for determining the range of a function, or any graph for that matter, that you should graph it first, as opposed to just trying to look at the equation and go, oh, well, I think the answers, remember range or the y values, the answers are going to just be between, this and this. If you have a very strong understanding of how transformations work, and this is an Algebra 1 lesson, so we haven't even gotten to that yet, unless you have a very strong understanding of how transformations affect a graph, do they move it left and right, shift it up and down, does it spread it out or make it more narrow or taller, and you've memorized a lot of parent functions, like you know what the basic parabola looks like, a basic line, a basic cubic function, a basic exponential function, then I really suggest that you graph that, you make a graph from that equation before you try to determine what the range is. But if we just have this y is equal to ab to the x and there's no fancy transformations done to it, it's just in this very basic form, we can see from these two sketches that they do go left and right forever, so the domain is going to be all real numbers. And the range, for this graph, the way it's drawn right now, is going to be y is greater than 0, because it's going, and I'm not including 0 because it's approaching that horizontal asymptote, which is the x-axis, or y is equal to 0. So it's going to approach 0, but it's always going to be above it, even if it's 0.0000001. So y is going to be greater than 0 and less than. Now, if you let x sort of decrease, or if you look to what this graph is doing as you go to the left, or as x decreases, the graph starts to shoot up to infinity. And actually, with this growth function, it's going up to infinity as well. So the range is going to be between 0 and positive infinity. If that were written in interval notation, you would see it written like this if your book is doing that. Okay, and again, the range can vary based on any kind of transformations or some transformations that can be applied to this equation. Now, one more thing. You see how that graph goes up forever and it's coming down, and it's not going down forever, but it is forever approaching zero, at least with the way these parent functions are drawn. That means, in a previous algebra lesson we just looked at, we talked about identifying graphically any absolute or relative maximum and minimums. Well, because the exponential functions approach a horizontal asymptote, and just keeps getting infinitely and infinitely and infinitely closer, but never really becoming that y value of 0. So because they approach that horizontal asymptote and they either increase or decrease, so we are either coming from infinity and we're decreasing until we approach, 0 forever, or we're letting x increase, or we're reading this left to right and the function starting to increase forever. Without bound away from the asymptote, the horizontal asymptote, there are no maximum or minimum values for exponential growth and decay functions. And again, just going back to this idea that eventually, especially in Algebra 2, you're going to be learning a lot about transformations and understanding how little sign changes and plus and minuses affect the graph. Eventually, unless you're watching this lesson as a review, you might see these reflected over the x-axis and be below the horizontal asymptote. But in Algebra 1, we're not going to need to be worried about that quite yet. So even though there's quite a few lessons already that I've done in the past related to this topic, we're going to clear this all out and do one example of reading a word problem, setting up an equation, and then graphing, or creating the graph that comes from that equation, coming right up. Alrighty then, our one example, which as I was writing this up, I just sort of had a new idea, so we're going to make it kind of like 1.5 examples by rewording it a little bit before we get into this one. After buying a vehicle, it loses half its value every 5 years, which for a lot of vehicles is actually kind of is pretty realistic. Assuming you buy a vehicle that costs $20,000, write a function that models its value over time and graph it. And we are going to work this all out, but I was thinking about how I was going to explain this problem without just saying, well, here's a formula, let's use it. I wanted to create a table of values. And then as I was thinking about how I was going to explain it, I thought I might want to help you set up a slightly easier problem first, which is we're going to say that it's losing 10% a year. And look at how we would set up that formula and then move into this slightly more complicated setting. Okay, well, first of all, what is going to be the independent and dependent variable? After buying a vehicle, it loses half its value every 5 years. Assuming you buy a vehicle that's costing $20,000, write a function that models its value. Okay, so clearly we need an equation that is going to describe the value of the car or the vehicle. And its value is going to be determined by two things. Well, how much did it cost in the first place? And what in here do we have some control over? Well, that would be how long we own it. So, and we see that there's some kind of variable of period of years here. So our two variables are years and value. And the years is something that we can control. So that's going to be the independent variable. And the value is going to be the dependent variable. Okay, so this whole idea of losing half its value every 5 years, it's going to be really easy to work this problem out with you on camera, because I'm just dividing by 2 for calculating half of an item, half of its value. But the fact that it's losing half every 5 years, that time period of 5 years, most interest problems are about on a yearly period. So that kind of complicates the problem just a little bit. So I want to change it to temporarily loses 10% a year. Now, what's going to make me think that this is exponential growth or decay as I read this problem? It's because we are not constantly adding or subtracting some kind of value, but we're taking half of something, or in the slightly reworded version, we're losing 10% of something. Well, to find 10% of a value, Like when you buy something, there's 7% tax. If you go to a restaurant, the standard tip is 15%. If you want to find a percentage of a number, you need to do some kind of multiplication. So either one of these problems has some kind of constant multiplication. And if you're constantly multiplying and some variable that you have control over, some independent variable here of time, is going to control how many times you multiply by something, then that is your tip that you were looking at some kind of repeated multiplication to an initial value. That's compound growth or decay. So our final answer is going to be in some form of y is equal to a times b to the x. Okay, let's make a table of values here for a second. If, again, for the slightly reworded version here, if you lose 10% a year, then years owned. Well, years owned is 0. I just bought it. Well, if you just bought it, then you spent $20,000. Okay, great. If I owned it 1 year, okay, well, if I owned it 1 year, then it's lost 10% of its value. Okay, so that means that it was $20,000, and we're going to then say, okay, let's take that $20,000, let's multiply it by 0.10. I found that by, this is a percentage, and we don't normally like to work with percents in percent form unless we're doing that part over whole is equal to percent over 100 formula. So I'm going to move that decimal back 2 places and make it, 0.10. And so 2,000 times 0.10 is going to be $2,000. So in that first year, we've lost $2,000. Well, my second column, and this is my independent and dependent columns here. This is what I have control over, and this is the output value. That's value of the vehicle. The vehicle is not $2,000. It's been reduced by 10%. So it's 20,000 whoops, missed a 0, minus 2,000, which gives us 18,000. Great. Okay. Well, now let's say we've owned it for 2 years. And please note that these are going to be, these are equal time periods just for convenience. And we owned it another year, and now it's going to lose another 10%. So that's going to be, well, now it's $18,000. We're going to multiply that by, I don't know why I wrote a star instead of a parentheses or an X, but we're going to take that 18,000 and multiply it by, again, 10%. And that is going to be $1,800, because multiplying by 0.1 really just effectively moves the decimal to the left 2 places. And now we're going to get the phone. No. All right, got that out of the way. Okay, so now we took the 10% of the 18,000, we got 1,800. Its new value now is going to be 18,000 minus 1,800, which is going to be 18,000 times 1,000 is 17,000, and 17,000 minus 800 is 16,000. Whoops, $100. I almost wrote an 8 there. Okay, and so on and so on and so on. Now, I need to tie this around, I'm showing you a pattern and showing you how to create this table, but I need to turn it around to letting you see how we get this y is equal to a plus b to the x. Okay, so I can see how, hopefully you can see how I'm taking some value, like initially we started with 2,000, I multiplied it by 10% to get the amount that we've lost on the value of the vehicle, and then I had to take that 2,000 and subtract it back from the 20,000 to get the 18,000, and then we had the same pattern here. The next year we had to base it off of 18,000 because it's basically like compound, well, it's exponential decay. Or if you're talking about increasing compound growth, now we're at the 18,000 and we lose 10% again. But we still see that same pattern of, well, it was 18,000 just like it was 20,000, and then we had to subtract 10% of that original value, only this time it was 10% of 18,000 as opposed to 10% of 20,000. So if we identify that as sort of like a general formula, when you want to lose 10% or calculate a 10% discount, there's some kind of, let's say here, original value, which we're going to call x, because here it was the original value was 18,000, and then here the original value, or calculating the next year's value, was 20,000. So there's some kind of variable initial value, And then we took that value and subtracted 2,000. We took that same value, we subtracted 1,800. Well, where did the 2,000 come from? The 2,000 came from, well, 20,000 times 10%. The 1,800 came from 18,000 times 10%. So it's some value minus, in this case, 10% of that value, right? And then if we look at least I hope you see that, right? We have 18,000, the original amount, at least after the first year of depreciation. Depreciation is the losing of a value on something that you've bought. And we're taking away that 10%, we're losing that 10%, which we found by doing 10% of, well, 18, or the 10% of the 20. So it's some value, subtracting 10% of that value, and what you have left, okay, if I put a 1 here, show that coefficient, 1 minus 0.1 is equal to 0.9x. So maybe some of you are on the back side of the camera going, okay, yes, I get it. If you lose 10%, your other part that you're getting to keep is the 90% of the value. So 90% x. So at time 0, we had $20,000. And at year 1, we took that 20,000 and we multiplied it by 0.9 effectively to get the 18,000. Let's see if that works. 20,000. Okay, and let's multiply that by 0.9 or 0.90, well, 0.9. Okay, let's see if we get that same 18,000. 0, 0, 0, 0. 9 times 2 is 18. Okay, but there's a 0.9 there, so we're going to have to move this decimal over. And yes, if you lose 10% value on your vehicle, then you can just do you can calculate the new value by simply multiplying by 0.9, because you're keeping the other 90% instead of doing this two-step process. And we get that 18,000. And if you want to repeat that process again, you're going to take 18,000 and multiply it by 0.9 to get to the 16,200. So we see now that as we go down the table in equal increments of 1 year, which matches the wording, my rewording of the problem, we're multiplying by 0.9 to get the next value. So at least with this setting, our equation would be y is equal to the initial value of 20,000 times 0.9 raised to the x, where the x, let's see here, to get to year 1, we multiply by 0.9 once. To get to year 2 from the initial value, we multiply by 0.9 twice. And if we wanted the value of the vehicle in 3 years, we'd multiply by 0.9, well, 3 times. So this is going to be the value of the car, and x is the number of years. Okay, now hopefully you can see that way that we've developed this exponential growth decay formula, y is equal a times b to the x. Let's look at the wording of this slightly more complicated wording of saying we lose half of the value. Now, losing half is a lot easier than losing 10%, because if you lose a half, you keep a half, right? And I have to teach you how that 0.9 came from. Maybe you would have known that anyway, but clear all this out. Look at this wording about losing half the value every 5 years. Okay, well, again, year 0, the value of the vehicle is still $20,000. At year 1, yeah, if I'm losing half every 5 years, then I don't, well, maybe initially have enough information to figure out easily what the value is in 1 year, because I only know that it loses half every 5. So making a table of values and saying, well, what's the value at 1 year? I can't just write that down. But if I put 5 years, oh, yeah, it loses half its value for 5 years. So half of 20,000 is 10,000. And if I put 5 years again, another 5 years, and make it 10 years total, then I lose half of that again. So now it's worth $5,000. And if I go another 5 years, make it 15 years, now it's $2,500. I'm just multiplying or dividing. I'm either dividing by 2 or multiplying by a half. So now I have a dilemma, and this is why it's important for you to state what your variables represent when you write an equation. Because is my equation, okay, let's see here, I want to put this in words now that we're kind of doing the real problem, okay, the value of the car, use a little function notation, is going to be dependent on some kind of variable, and it looks like we're starting with our initial value of 20,000. We're constantly multiplying by a half. Okay, you see that y is equal to a, b, and now we're going to bring in some kind of x here. My x, which is going to be the independent variable, or represented my independent variable. Well, if I let the independent variable be the number of years I own the car, then I can't just put years up here as my independent variable, because you can see after 5 years I didn't multiply by a half 5 times. I only multiplied by a half once. So I need to take, if my independent variable is going to be just simply the number of years I own the car, then this exponent needs to be, well, the number of years I own the car divided by 5. That is a correct form of my equation. Now that looks a little bit more complicated because, you know, the basic form I just gave you was y is equal to ab to the x, and here we have some kind of variable being divided by 5, so my exponent is slightly more complicated than what was in our form in the definition. And that's okay if this is how you're going to define your independent variable. Now if I want to simplify the look of this equation, like, you know, a student could write this. And it could be right. But I just said that you couldn't just simply put an x there. Well, how are you going to define your variable? Like, you know, if I say let x equal the number of 5-year periods, that is going to be an appropriate definition of what x will be to allow this formula to work. I was going to try and write the word periods, but I'm not going to fit. So, and let's let that be our x, okay? So the value in terms of x is equal to 20,000 times 1/2 x, or you could write the value of, in terms of the number of 5-year periods, is equal to 20,000 times 1/2 raised to the number of 5-year periods. And that's what this is doing as well. If you just let x be years, and then you take those years and you divide by 5, you're going to get the number of 5-year periods. Like 15 divided by 5 is 3 5-year periods. And we multiplied by half once, and we multiplied by a half, twice, and then we multiplied by a half again, 3 times. So you need to define your variables so that, you know, your teacher will know if you wrote the correct equation or not. That's some of the, you know, what's interesting about word problems, and it's also what makes it a little bit more difficult. You have to think more. Okay, so we're going to focus on this simpler form of this equation where x is the number of 5-year periods, because, well, that's what we're doing, that's what's happening in the problem. And let's finish up the graph and call this video done. So we draw an xy axis. Okay, well, that's all great if we don't have a word problem and we don't have any kind of real context, and I'd want to sort of draw those xy axis kind of big and talk about quadrant 1, quadrant 2, quadrant 3, quadrant 4, and have, you know, the possibility of having negative x's and y values. But this is a word problem, and it's not possible to own a vehicle a negative number of years, and it's not possible for the value of the vehicle to be negative. Now, if you buy a new vehicle and it loses value faster than you're paying off the loan, you might owe more than the car's worth, but the car's value is still positive. So we need to have, let's see here, We really only need the positive sort of quadrant 1, if you will, of the xy axis. The horizontal axis, the independent variable, the thing that you have control over is the number of years you own the car, but in this case the x-axis is not going to be the number of years. It's going to be that darn phone again. It's going to be the number of 5-year periods. So let me get the phone, I'll get this set up, and we'll be done. Sorry for the interruptions. Alrighty then, let's see if we can finish this before the phone rings again. Alright, so we have our x-axis labeled as number of 5-year periods. We have the value of the vehicle in dollars, with the scale on the vertical axis as well, independent variable, dependent variable. Let's see here. I saw that the initial value of 20,000 is quite large, and remembering that table of values went 20, 10, 5, 2.5, so I just decided it would be good to count by every $5,000. So at time 0, we had a vehicle that was worth $20,000. That's when you purchased it. At 1 year of ownership, or not, excuse me, 1 5-year period, that's actually 5 years of ownership. 1 5-year period later, we had a value of $10,000. And see, we do need to write that, hey, this is the number of 5-year periods, not years, right? Because I just said that that would be a 1-year period, and it's not. So we have 2 after 2 5-year periods. Then that half of 10,000 is going to be 5,000. At 3 5-year periods, that would be half again, which is going to be 2,500, and then half again. Half of 2,500 I think is 1,250, and this is just going to keep approaching. Now again, the value of your vehicle is never going to be negative. This is approaching a horizontal asymptote of y is equal to 0. And then now remember, this is not 6 years, but 6 times 5, 30 years later. Okay. The domain and range of this graph, the domain is going to be that, at least in terms of this word problem, ownership of the vehicle, is going to be that x is greater than 0, greater than or equal to 0, and less than infinity, and because it's going to just go on to the right forever. And if it was just a exponential function that had no real life context, of course, this could cross the x-axis and continue up to the left. You saw that earlier in the lesson. The range, well, you can buy cars that are, hundreds of thousands of dollars, millions of dollars nowadays. So $20,000 doesn't seem like much, and the range, again, just a naked exponential function curve would be from, basically 0 to infinity. But our initial value was $20,000. So our range is going to be where y must be greater than 0, because it's approaching that horizontal asymptote. It's not going to actually become it, and less than or equal to $20,000. Now, I really don't see a reason why, you kind of do want your independent variable, I believe, to match what is on your x-axis. If we were to have instead focused on this as our equation, and x were just the year, and our exponent was years divided by 5, well then, of course, we could change this scale and have the x-axis be time in terms of years, but then of course, how long did it take for that $20,000 vehicle to become $10,000? Well, that was 5 years, and then this would be 10, 15, 20, 25, and 30, and so on. And really, this is how we talk. I mean, I guess if you're used to financial work, saying number of this particular time period would be great. But it'd be much more easy to understand if you just said, okay, the x-axis is the number of years, and do that division of 5 in the exponent to sort of let the formula create the number of 5-year periods, and then you can just look at the graph and go, oh, 5 years later, $10,000. 10 years later, $5,000. And if this were on a calculator, and you could just, well, we could put 1 for 1 year and then work out the arithmetic, or we could put this on a graphing calculator and hit the trace button, and we could trace it to where it gets to an x value of 1 and see what the y value is and know what the value of the car was in 1 year. That is the end of my lesson. Oh, by the way, this idea of constantly multiplying by a number to create, like what was that table? That was 0, 1, 2, 3, 4, 5, and we are creating a list of numbers based on repeated multiplication. Now, later on in your math studies as well, you're going to learn about two special type of sequences, arithmetic sequences and geometric sequences. A sequence of numbers that are created by constantly multiplying by some value. In this case, we were constantly multiplying by a half, or that first sort of reworded example, constantly multiplying by 0.9. That's a perfect tie-in to setting up a geometric sequence. So I'm going to have that lesson in the description of this lesson as well if you want to learn about geometric sequences, because it is a list of numbers created by constantly multiplying by the same value. I'm Mr. Tarrou. Bam! Go do your homework.